The final result of today's lecture is a possibility that may be surprising to you, and that possibility is that if you measure a particle and you find it at a position, say A, and then you again measure and you find it at a position B, and you think it has traveled between A and B, but actually quantum mechanics say that it cannot travel from position A to position B. Oh, that's a result, and the result is of a calculation. So as far as calculation are concerned, in that regard as well, the today's lecture is special in that for the first time in this course, we have to solve Schrodinger equation with the potential. That's like in Newtonian physics, you given a formula for force and you find Newton's second law. So that kind of thing here, rather than force, we are giving a potential, and rather than Newton's second law, we have to solve a Schrodinger equation, and that is also this calculational aspect is also starting from this lecture. So both from a point of view of a result and for calculation, that is a very crucial, important, and interesting lecture. There are reasons for to listen it, and I tell you what is in detail in it, and that's the outline, and that is that first we have to solve Schrodinger equation for zero potential, which is called free particle case, and in that case mathematically the simplest result is which is called plane wave. But this would be an approximation, because actually a quantum particle has two wave packets. So the comparison between wave packet and plane wave, that's the first thing to talk. And then we have to use this for a potential which has two values. Both are constants. One can be taken to be zero, other non-zero, and that's called you can say case 2. The first was potential 0, and then 0 and non-zero, that's case 2, and that is called step potential. And there we have to calculate what are called reflection and transmission coefficients. So wave reflects and wave transmits here. And having introduced that's next we go to what I started talking about as a result, and that is a barrier. The question is called barrier, and barrier means that you have three regions. You have two regions of potential which can be taken to be zero. In between is a non-zero potential. That is a calculation case, and the result of that is called tunneling. And tunneling is what I started in my first sentence today was that particle can appear from one place another place without traveling between them. In tunnel actually you travel, but in quantum mechanics when we say, we mean it that it's without traveling. And then I have to tell this can be since that can be a surprising result, so it's good to know that has an experimental verification as well, and that is called alpha-radioactivity. So that's the whole plan. Now coming to the details, as I said, first I have to deal with the Schrodinger equation. There's a time independent Schrodinger equation because potential energy is zero, and that potential energy is time independent, so I'm using time independent Schrodinger equation. With potential energy zero, it becomes a simple differential equation. You take this minus h bar square by 2 to the other side. You on the left hand side you keep only second derivative, and on the right hand side, whatever you have it, you have to think of that if it is positive or negative. Because it's a negative, so I leave negatives separate, and the remaining positive quantity I name it k square. I want to keep k as a physical quantity so that its square is positive, and I have to tell you what is the significance later, why it has to be physical quantity. But for the moment you just take it has to be physical quantity, so it has square is taken to be positive. That's how it is defined. Now here is the differential equation. It appears so much times that you better guess, or if you cannot yourself guess, then worst case could be that you memorize, because even memorizing is not that much bad, because this appears many times. So even if you have memorized this result, but better you guess it. So I take you that. What is the function that if you differentiate twice it doesn't change? One is trigonometric function, sine and cos. twice differentiate, and but if there's a k in angle, that comes out twice, because this is the second derivative, and the negative sign is a calculus, you know it. Now that's mathematically there can be other option as well, but if I choose that option, that means my psi, small psi, that means that's a time independent factor, that is real. And if that psi is real, then the probability current is zero. I have shown the expression, and that was my previous lecture. You can stop and see calculation yourself, and this is simple to tell you the result is zero. And if the probability current is zero, that means the particle is not traveling. But if I want to, my boundary conditions are so that way I'm talking about a particle which is moving, because I said it particle. My very first sentence of today's was that it appears at one place, and then apparently it has to move to other place. If moving becomes impossible, that's a technicality, I can deal with it. But I have to talk about at least incoming particle which is moving. And moving means the probability current is non-zero. If it is non-zero, the way to get non-zero is that, when I talk about, I ask you what is the solution to that, you to guess. Sorry, I don't again ask you to guess. This time you guess the solution, not trigonometric, not sine, not cos. Do you know any other solution that you take it and then again you take second derivative and the function appears again? And the answer is exponential, e power iota. Exponential doesn't change. Even first derivative doesn't change, second derivative also doesn't change. Every time you have iota k and same, and appear same. Iota square gives you it's a simple calculation. You can verify that if that is substituted here, this differential equation, blue differential equation, is satisfied. Now this time the benefit as compared to the previous I took trigonometric, and now this time it's not trigonometric, exponential, and the benefit is that psi is small psi is the time independent factor, and if you combine with time dependence, when I derive time independent certification, I told you the time dependence is minus iota omega t. You combine with it, that is a capital psi. That's the difference between capital psi and small psi. Whatever you take it, because this is not real, so probability current is non-zero. And here we interpret it: if it is plus, it is right moving; if it is left, if it's a minus, it's left moving. And that you can verify by actually calculating probability current. If it is plus right moving, then probability current is positive, and if it is minus, probability current is negative. I have shown the calculation in the previous lecture, but it's not necessary to do calculation again. It's just simple thing. You can even memorize, remember that the plus is the right moving and minus is left moving. Although it's a simple calculation, it's just one line calculation if you want to do it. Okay, now I have to deal with one technicality that what I have shown you a result that was a plane wave. Previously what I showed you, that's a plane wave. But for a plane wave, normalization constant is zero. I've done a calculation. It's a simple again integration, and it's simple one line calculation, that is a is equal to 0. And if a is equal to 0, you go there. If a is equal to 0, psi is equal to 0. That means psi square is also 0, and that's the probability density is 0, and that's probability is 0. And probability is 0 means it's impossible. So in principle, we are talking about something impossible. And that is the first question I have to deal with, that. First technical question is that. And I have to clarify that this probability density became 0 because became impossible because I was using an approximation. In actual calculation, I should have not used plane wave. I have used quantum mechanical particle is not a plane wave. Quantum mechanical particle is what is called wave packet. I have a full lecture on that. But if you have not heard lecture, don't worry. You just see it in this sort of movie. In GIF, you can see that is a not a plane wave. It's not a plane wave. It's a wave packet. Packet is there are many plane wave. And the result which you can see, it has a finite width. and calculation says it's called Fourier transform, if you know it, and I have also tell you, but if you have not seen that video previously, don't bother, you just take my word for it. You can take my word if you have not seen video, and if you don't know Fourier transform, that if you want a finite width, your energy has not to be one. There will be many plane waves, that means many energies. So there has to be a width of energy that I've shown you slightly, is a 13 to 15 width. So this means energy has a spread in actual wave packet. Now one thing I should tell you, that many people say that quantum mechanics says that you can be a quantum fluctuation, that energy can violate. That is wrong, okay? In my opinion. That the proper is that, it's a spread of energy. It's not one energy, it's a 13 to 15. It's a range of energy. If you call range as a spread, that's right. But if you call range as a violation, that's wrong. It's a violation in that once you measure it's a 15, next to measure it's a 14, again you measure it's a 14.5, again you measure it's a 13.5. But there's no violation. There's not rule. Energy is not violated. It remains conserved, but it's only spread at different time. It appears. Right? So that's a technical side issue as well. That don't call it violation, call it spread. But maybe I can take you back to the. Okay, this time I think I've stopped it here, and you can see it. You can concentrate. It's a spread, not any violation, because the energy, if you see it, energy is here, and that's a constant. There's no the violation of law of conservation of energy. So energy is constant. So it's wrong to say quantum fluctuations give you energy fluctuation. Energy is not fluctuation, it's a constant energy. So it's actually it's a spread, which if someone calls it a violation, it's I would say, I should just say that I say it's wrong. It may be something in a popular science which is not in technical science, but it's wrong. In technical science, actually, it's a constant energy, and constant means it's a horizontal line. It's everywhere. Okay, maybe I start doing actual calculation rather than clarifying a misconception. And now go to start actual calculation, and that I said that the first case I had taken Schrodinger equation was V is equal to 0 throughout. And next case is that V has two values, and one value, the other value V naught is larger than the first value, and like in classical mechanics, only changes of energies are measurable and energy is not measurable. So you can choose energy in the left region to be 0, and the right region it would become V naught. And I'm taking the case that V naught is equal to positive. And I'm taking the case that total energy, which is constant, and I've spent maybe many minutes on telling that it's a constant energy that is greater than V naught case. It could be lesser, but that's a different case, but I cannot include all calculations in my one lecture. So I have done a selection of this case, and total energy is a constant total energy is greater than step. It's called step because of the shape of the graph. The shape of the graph is a step. And what we have, so this is your question. This is potential. With this potential, you have to solve Schrodinger equation. And when you solve it, eventually it's a science. You have to calculate a quantity which can be measured. You can say wave function, but wave function is a complex quantity. It cannot be measured. Square is a probability density. Probability can be measured, but it's a very difficult measurement. So what is manageable measurement is of what are called reflection and transmission coefficients. And these are, reflection coefficient is the modulus, absolute value of ratio of reflected current and incident current. And I have to take approximation that reflection means okay, maybe I start with incident. Incident means a plane wave which is coming from left to the boundary. I'm using the approximation that it's a plane wave, and I've told you actually it's a wave packet, but I'm approximating it by a plane wave. And when for plane wave, I've shown in previous lecture actual calculation. That was what is the expression for probability current, and you don't need to know the actual detailed expression, but you just take the result of probability current, which I shown you in this lecture as well. You can calculate for incident plane wave incident probability current density, to be precise, and similarly for a reflected wave, which is B, and you take the ratio and take the modulus, that is called reflection coefficient, and somehow that is measurable quantity, practically measurable quantity as well. And the transmission coefficient is the same, except that in numerator, rather than reflection, you have the C, the transmitted wave. It's again taken to be plane wave. You know, it's K1, its wave number is changed. Actual calculation tells why it is changed. And you take the ratio, and this is called transmission coefficient. So again, the wave number is changed, so the wavelength is changed. You can see it's the wavelength here, it's a different wavelength here. But in this, in reflection, you see K1 is the same K. So K is, wave number is 2 pi over lambda. This means same wavelength. Actual calculation, I tell you why it is same. But it's same in picture, you can see as well, it's the same wavelength. And as I said, J, if you know plane wave, you can calculate J, and this calculation I did in previous lecture. But it's a simple one-line calculation, and if you have not seen, don't worry. I'm showing you the result here. That for a plane wave, you have to take normalization constant square, and you multiply with the h bar, and k is the wave number, and divided by mass of the particle. Okay, it's a zero normalization constant, but that I have already told you that it's actually an approximation, otherwise it's a plane, it's a wave packet. And you take transmission coefficient, because that's the ratio of probability current, so that means it's a ratio of k's, and it's a ratio of normalization constant square. And you take the ratio, you know, when I said it's a normalization constant is 0, that created a problem. In principle, the solution is to take plane wave, but to pay wave packet, but rather than going into that complications, you can remain using plane wave. In that case, one can say your normalization constant is 0, but there's a solution to it. We are not finding normalization constant, we are finding ratios of normalization constant. So if both are 0, then the ratio of 0 can be finite quantity. Just like in derivative in calculus, you have dy over dx is approaching to 0, and dy is approaching to 0, but the ratio can be non-zero, and that is what is going here. Both are 0. I said normalization constant are 0, but the ratio is non-zero, and in this limit, ratio is approaching to, calculus term is ratio is approaching to a finite quantity, and that is a measurable finite quantity, and that is our topic of calculation, target of our calculation. Now calculation I start now, and that will also tell you why k's are same and why k's are different, and these are things in detail which I did not only spoke and not gave you reason. Now it should be full reasons, full calculation reason, and the calculation start with first is choosing potential energy in the left region. I take it left right. Now there's another choice comes between left and right is a boundary, and I choose origin at the boundary, and a potential energy in the left region to be 0. With both choices, choice of origin and potential energy, this becomes your potential becomes what is called piecewise function. That for less than x region 1 it is 0, and for greater than less than 0 its potential energy is 0, and greater than 0 for x greater than 0 is region 2, and potential energy is V0, which I take to be positive. In region 1 here it was 0. I have not shown you, need not show. Differential is not new. I have already done calculation for what is called free particle case. Only difference is that rather than k, I have renamed it k1, because this time the calculation, in full calculation, it has to be make a distinction between another k. But otherwise, nothing new, or I hope it's okay if we don't spend time on it. This expression is also, I've spoken maybe 5 minutes or 10 minutes ago, and incident. Okay, here, okay, that's something new. Why I'm calling it incident? It's plus iota. That means J probability current is positive, and it's right moving, and that's why right moving A, and that's incident coming from left. And in this, the second term, minus means J is one line calculation. The result is that J is negative. J is negative, that means it's a left moving. It's a returning or it's reflecting. Okay, that is for left region. And now for the right region, you have, rather than 0, you have V naught potential energy. When you simplify it, you again take to the standard form. That means you collect the second derivative on the left, and the right, rather you had E at this time because V naught. So rather than E, here it was E, and here if you take V naught to the right hand side, that means here is the V, and here is E, and here E is replaced with E minus V naught. So in your this simplified form as well, or maybe standard form you call it as well, this E is replaced with E minus V naught. Now before defining it, it's crucial that you define only quantity which is positive, and that's k square, because I want to keep wave number as a physical quantity whose square is positive. And this time you remember E is greater than V naught, so E minus V naught is positive, so that quantity is positive, and that I called K2 square, and minus I have shown it separately. Now I do calculation with that choice. Again, second derivative, and here it was K1, here it would be just only the difference is K1 is replaced with K2, and you would say it should be same with plus, and there should be with minus as well. Okay, there's no reason that this normalization constant, they are same, so I cannot assume it without calculation, so I've kept a second, it's a separate letter. If they are same, my calculation should tell you. I should not put it by hand. So I've renamed it as a different. So I should have it here, rather than A, C, rather than B, I should have D. But D I have not shown it because D means, this minus means it's a left moving, but in right region, left moving, and that would be coming from right, and my boundary condition is that there's no source on right, so that means there's no D wave. So actually we have only A, B and C waves, and that's a good, the counting is good, because next if you see it here, if I go you think of that, how many unknowns you have it in calculation. K1 is not unknown, K1 is energy, and we suppose if energy is known, then we calculation. So in that sense. And similarly for K naught, we were doing calculation only if V naught is known. That's our problem. But the new thing has appeared is, which is A, B and C. You have 3 unknowns. So maybe you may be thinking that for 3 unknowns you need 3 equations. But what you have to find are reflection and transmission coefficients. That they are ratios. So A, B, C, 3 quantities, but how many ratios do they make? I'll show you again. I just asked you. The ratio is, one is the ratio is B over A, and one is C over A. So that's it. So you need actually 2 ratios. That means you 2 unknowns, and you need 2 equations. And the equations are obtained in the following way. And that is that wave function has properties, because wave function has to be continuous. So continuous everywhere, that has to be continuous at the boundary. And the continuity definition of calculus is that left limit has to be same as right limit. The left limit is, this is green, and the right limit is which I shown in blue. And the left limit, because it is at x is equal to 0, you put x is equal to 0, that becomes A plus B. And the right, if x is equal to, that becomes C. So left limit is equal to right limit for wave function, that becomes first equation. And the second is also the wave function's derivative is also continuous, because second derivative exists in Schrodinger equation. So if first derivative is continuous, you differentiate and then you take x is equal to 0. You differentiate here, you get iota, extra iota k multiplication. Higher differentiate, you get minus iota. Sorry if I spoke x. It's differentiate with respect to x, so we get iota k1. And here you get minus iota k1. But otherwise you put s equal to 0, so they're same. And here again, your differentiation will give you iota k2, but otherwise c. So you have two equations, two unknown, and now it's a case of algebra. I don't know how many details I should spend. For completeness, I spend some time, but actually, if you are only for understanding then result, then it's only algebra. Anyway, still I spent some time on it. If you have two equations, and normally it's it's called linear algebra. Algebra approach is you add, you eliminate one quantity, you subtract, you eliminate another quantity. But okay, if you have to do that, you better divide the second equation by iota k1, so that here you have a, and here you have b, and you add that b is eliminated. You have only a and c, their ratio. This is one line calculation, you do it, and I think I've almost spoken it. Otherwise you can do a pen and paper and just one line and you do it, and you get c over a ratio because b is eliminated, is that. Okay, now you have to get, c over a, c is transmitted and a is incident, so that will give you transmission coefficient, and now we have to also find reflection coefficient. That means we need ratio of b over a. You can b over a, you can do a lengthy calculation that you as usual it would be, you subtract it, a is eliminated, you get ratio of b and c. But this is easier is that your first equation you divide by a throughout. You say that 1 plus b over a is equal to c over a. So that will give you c over a. Okay, what we need is b over a in terms of c over a. We already know c over a, so you do a calculation over b over a becomes that. That's again one line calculation you can do by pen and paper yourself. I've almost spoken it. Okay, now what I've taken, showed you the ratios, and then for a presentation I have to put these in promised reflection and transmission coefficients. And reflection coefficients, they are ratios of probability currents, and the probability currents for plane wave are k multiplied amplitude square, and the ratio is k ratio, but the k is same here, k1 and k1, so the k ratio is 1, and the amplitude ratio is b over a square, and that is b over a. I showed you, that's one side. That's reflection coefficient. And as far as transmission coefficient, you say this time because k's are also different, so you have k ratio as well. So k over 2 over k1. C over a I showed you in previous slide. All in all, you simplify, you get that. So that's all. The first case is complete. Now some optional indications are there which can help you develop a common sense. Common sense is a risky thing in maybe on every side, but especially in quantum mechanics. But if you have done proper calculation, and then to remember calculation, you develop a common sense, there's no harm in it, and that I'm going to do. I'm not replacing common sense for actual calculations. I'm not making a common sense excuse for not doing calculation. I've done calculation, but now I have to, if I'm in a seminar or if I'm reading a book or so, and I cannot do calculation again and again every time, so it's good to develop a common sense so that you can remember result, and for that you note it. You develop a quantity k2 over k, you divide by k1 numerator and denominator, and you can express this in terms of calligraphic k. This becomes that, and the same thing you done here, you divide this time by k1 square, numerator you have k2 over k1, that I have gotten calligraphic k. So your results become that. Your calligraph k is k2 minus k1, and you see the definition of k2 and k1 just 2 slides ago, and you can scroll back and see that you have this result. And now everything, if you now having results of reflection coefficient, transmission coefficient in terms of eventually which are characteristic of a case, that potential energy, you see, you consider two special cases that maybe three. One is you add them up. It's a simple thing. You take square and square, and okay, minus 4k plus 4 cancel. All in all, they add up to 1, and that's a common sense. some percentage is reflected, some percentage is transmitted, and the total is 100%. That's one common sense I tell you. Another common sense which you can develop, can or cannot, that's why I optional. That if you take the case when V0 is equal to 0, V0 is equal to 0 means there is no boundary. No boundary means V0 is equal to 0, this means your calligraphic K becomes 1, and here is 1 minus 1, R is equal to 0, and the T is 4 divided by 1 plus 2 square, 4 divided by 4 is 1. Or another could be that when R is equal to 0, that equation tells you that R is equal to 0, T is equal to 1, whatever it is. That means no reflection. So that you can develop a common sense is that there is no boundary, there is no reflection. There is no reflection, sorry. I was thinking something else. There is 100% transmission. Wave comes and wave is here. Quantum mechanics, you cannot use classical particle language, that's risky. But wave, it's a minor difference. You treat every particle when it's moving, it's a wave. And wave is like your common sense wave. The only thing is that your common sense wave carries energy, and here it has to carry probability. But before making a transition from energy to probability, you can use your common sense well if you want to avoid calculation. Just like a wave, a wave is coming, wave is traveling. You can use it. You can even avoid some calculation, at least repeating calculation. And if you think of that, maybe if you have well common sense, what will happen? If V0 and E become identical, that means there is no gap in which the wave has to transmit. So what will happen? Think of that if your common sense says that, and I show you the result. The result says that in that case, because E and V0 are same, so here in the ratio that becomes V0 over E is 1, so 1 minus 1 is equal to 0. So your calligraphic K is 1. So R is 1 minus 0, 1 plus 0, R is 1, and T is proportional to K, and when K is equal to calligraphic K, and when calligraphic K is equal to T is 0. So R is 1, T is 1, so that means 100% reflection. Now I don't know what your common sense told you, but that is what it is. If there is no gap in which to transmit, there is no transmission, 100% reflection. You can use things to develop a common sense. I am repeating now, same thing. I go to next case better. Next case is the question. Question is called, the first case was a free particle, V equal to 0 throughout. The second case was a step in which you had 0 and V0. The third is you have potential energy 0, 0, in between V0 and again 0. So you have 3 potential energies. Although the special case is that 2 are same, and I can take 2 to be 0, and in between will be V0. And this time the new thing is, one new thing is that you have 3 regions rather than 2. Another new thing is that V0 is greater than E. I mean, V0 less than E case is also there, but I don't have time to do that. You can see in many books this case as well. But I have to do some selection, and my selection for some reason or other, and I tell you why I have selected the case that this time the V0 is greater than E. Okay, this is called barrier, and I hope you can see that there's a shape, because the graph of the potential is barrier. It's a hurdle that if you want to travel from here to here, it's a barrier, because it's a hurdle there's a barrier that will stop you. That's just to remember the shape is a name, if that helps. Another word is the case name is symmetrical. Here the symmetrical means the potential energy, in principle you have 3 potential energies. I could have called it V1, V2 and V3. But what is happening is that V3 and V1 they are same, and they are taken to be 0. When they are taken to be same, right same as left, so that is a symmetry. So that means symmetrical barrier. So that's I think I have pinpointed my case. And now what I will say about case. To say about case, I have to translate what I spoke in mathematics. In mathematics, potential energy is in writing it's piecewise. In the previous case you have 2 pieces, and now you have, because 3 regions, you have 3 pieces. This is region 1 piece, and I've chosen origin to be at the left boundary. So this means right one region 1 is s less than 0, and here potential energy is chosen to be 0. As the right region start x greater than 0, but till x is equal to a, that's region 2, and in that its potential energy is V0, and after a it becomes 0. So now what I spoke, now I have translated that to mathematics. Now with that potential energy I have to do calculation, because there are 3 regions, so I have 3 calculations. So in the leftmost V is equal to 0, so there is nothing new. I have done it twice already. This calculation I can, I think, save time speaking about it. The region 2, it's also not okay. Apparently it's the same as I did in previous case. But remember, there was one crucial difference is there. If you remember, you are doing physics. The previous case when I had E0 and V0, I kept minus separate, and the remaining quantity I called it K2 square. And that word was useful physics if that is a positive. But this time you remember, is that quantity positive? Think of that. I can't take you here, but I just can tell you that in the graph V0 is greater, so E minus V0 is negative. So negative quantity, I would not like to define negative quantity as square, so I have to include this negative as well. This whole quantity, that is a positive, and that I call beta square. Now I've chosen the letter beta, not K, because I want to keep the K for plane wave number, and this beta is physical interpretation, is not a wave number, and the reason is that wave number is for a sinusoidal wave or a traveling wave. But this time you see what kind of wave it is, and if you think of that, then you note it that your second derivative is positive. So that means if you take sine or cos, they will return you minus. Exponential of iota, that is also give you minus. So this time it's something new. And I show you the result, you can simply verify by trying. It's e power beta and e power minus beta. No iota, no sine cos. And that means your psi is real, and if psi is real, the probability current is 0, that it's not traveling. And that is the whole thing which I very first sentence in today's lecture I said. Particle cannot travel, it can go from region where it appears. My very first sentence today was that it appeared in region 1, appeared in region 2, and you think it traveled from region 1, it traveled to, but you know, in between is region 2 and traveling, but you know, probability current is 0, so that means it cannot travel. So that's the whole thing. If you have understood it, maybe that's the main lesson today. But if you have not, then I have to continue. That, you know, I've spoken it. There's no traveling between them, but it's still okay. In region 3 as well, I think if for completeness I should say region 3. Region 3 is the same as is a V is equal to 0 again. So the calculation is as in region 1, and again I replace A with you know, I've C and D I have already used up for region 2, so I have the letter E and F, but E is maybe confused with total energy, so I have replaced with F, and then I should have G. But you know, F e power iota, that's the third region plus, remember what it is, it's moving to right, so in the third region moving to right, that's a transmission. But with minus G, e power minus iota, that would have been third region moving to left, but there is no source on right, so that my boundary condition says that there is no G term, so that's, now you have, now coming to actual calculation, how many unknowns you have. K is not unknown because there is energy, and we have to take, actually whatever you call it, energy and K is related. Once you find K, you find energy, or once you know energy, you know K, so in that sense it's not unknown. Your unknown as at least as before, if you can, in that spirit, your unknown have A, B, C, D, you may count it, 4 and F, 5, but we have to find probability and transmission coefficient, their ratio. So how many ratios you have? A and B not 2, the ratio is only 1, B over A, C over A, D over A, remain counting, F over A, how many? 4. So for unknown, you need 4 equations. And now this time, the doubling of equations, previously you had 2 unknown, 2 equations, and now there are 4 unknown. You get 2 more equations because you have, in the previous case you had 1 boundary, and 1 boundary gave 2 equations, and now you have 2 boundaries as 0 and a. 2 boundaries and 2 boundaries means for every boundary you have 2 equations, 2 boundaries means 4 equations. It's a calculation, I'm not sure if you're interested or not, but for completeness I have to comment on that. The left boundary is nothing particularly new, x is equal to 0, so I think the calculation are same, except that previously you had iota k2, and rather than iota k2 I have beta. So the right boundary x equal to 0, that is something new, so maybe I should speak about something. It's a continuous x equal to 0, that means the right boundary between region 2 and region 3. So that means now it's a pink versus blue. Is a pink, you take x equal to a, that's the left limit of second boundary, x equal to a. It's the same, you put just x is replaced with a. And the right is just x replaced with a. So I hope there's nothing to be explained. And differentiation, the result, and derivative is also continuous. You differentiate it, you get multiplication with beta, and here multiply iota. I hope it's a simple differentiation, and you get 4 equations, 4 unknown. And I'm not sure if you like me spending time on explaining the algebra, but maybe some of you want, so I make some comment on algebra. Others may be interested only in the result, but they bear just 2-3 minutes of algebra explaining, and that is because some students may need that. Algebra is the following: that you divide by iota k, that means here becomes k, here is a b, and you can eliminate b, but your c and d are left. So that means you express a in terms of c and d. That is if you add. And if you subtract, a is eliminated, you have b in terms of c and d. And with that, now that's the first 2 equations used. And the second 2 equations, they give you that, and if you, again you divide by beta, and then they become same, c here, no beta. You add it, d is eliminated, you have c in terms of f, and you subtract, d in terms of f. Now remember, just in the last minute I spoke c and d, but in the previous, maybe 2 minutes ago, I said c is known. Okay, I spoke the other way. A and b are known in terms of c and d, they are related. So from c and d in terms of f, and then c and d are related to a and b, and I think maybe most of you would not like me to spend more time on calculation, because the structure is understandable. You have 4 equations for unknown, you can solve it. I don't spend time on explaining the solution. Eventually you can find any ratio, and now you come to physics of it. Which of you have 4 ratio, b over a, c over a, d over a, f over a. But what we want this time, I want only transmission coefficient. I don't need reflection coefficient, because I can use the result, and next I can prove it generally as well. The reflection plus transmission coefficient is 1. So if you find one of them, you find the other one. And next time I choose to find transmission coefficient, and that is the ratio. Here is the transmission, here is incident. Transmission is f, incident is a. So the transmission coefficient is f over a. But do you remember not? It's a square. And also k ratio, but k, you say k is same as in green and blue, so k is same, and I've told you the reason. So k ratio gives you 1. So f over a ratio is our transmission coefficient, and now I show it. I think the symbols are there and nothing new, and I just show the result. Okay, sorry, result is very lengthy, tedious, I don't show it, but only I discuss one thing. You can find the result in any book. I tell you, for example, quantum mechanics by exactly from the RIT, or you can Google it and you find anywhere. The topic is, the keyword would be barrier, or you can see the expression. It's a lengthy expression, maybe it's not interesting, but what is interesting is that the particle is traveling here and is traveling here, but in between is not traveling. So how it could be that that is not traveling between and is traveling to left and right? Now, if someone says that this means that you can, if you have an ordinary barrier or hindrance, or maybe you take it to be a wall or anything, you cannot travel in between, but you can go from left to right. You have a wall of your room, you can go to the other side without traveling inside. You may see, I mean, if that is the case, that would be a violation of experience, our observation. And quantum mechanics have to give an argument that quantum mechanics is not against your experience, your observation. Your experience does tell you that you cannot cross a boundary, cross a wall in your room. Does quantum mechanics say anything against that? The answer is no, because when you say about wall in your room, you're talking about daily life. Your velocity and quantity, they are much greater than Planck's constant. So that limit is called classical limit. So if quantum mechanics you are not that much used to, then maybe easier comparison of classical and modern physics is through theory of relativity, which is conceptually is easier than quantum mechanics because the language is same. So if you want me starting from your rather familiar relativity, then I would say relativity. Classical daily life limit means that your speed is much greater than speed of light. That means you can take speed to be zero. Another thing you can say that whatever is speed in comparison to that, your velocity, speed of light is infinity. There are two ways of saying it. Either you keep c to be constant and you say that your velocity is much lesser than that. Velocity is approaching to zero. Or you can say that whatever is your speed, c is approaching to infinity. That's classical mechanics. Now eventually you have to take quantum mechanics. In quantum mechanics, your daily life quantities, they are much greater than Planck's constant if you make a appropriate combination so that units are same. And alternatively, you can say that keep the numerical values of your daily life as well, because you have to make physical prediction and you keep numerical value. And rather you say that because they are much greater than Planck's constant, so you can say Planck's constant is much lesser than zero. That is approaching to zero. So that's the meaning of classical limit. And now if you do the calculation, which I have not shown you the result, but I have explained how to do it, f over a ratio, and you take h approaching to zero in that calculation, then the result is this transmission coefficient for daily life is zero. This is a quantum mechanics result. So that means quantum mechanics does not clash with your daily life experience. So this has no observation clash. So that's just a defense of quantum mechanics. And now, before something like you can say attack or so, that not only that quantum mechanics is not wrong, it's also that quantum mechanics is useful. It makes a prediction which is verified, and that's alpha radioactivity. But before going to that thing, which is a positive argument for quantum mechanics, I spent some time on an optional topic, and that is I use that reflection plus transmission is equal to 1, but on that I proved it only for a special case, which was I think my first case, which is today called potential step. But I indicate that the result is not limited to potential step. I've already used it for barrier. And why I've used it for barrier? The answer is that I prove it generally without depending upon step. That generally reflection plus coefficient, transmission coefficient is 100% is 1. And the general proof is the following. Incident current is that expression, and that expression is not for any special case. That's the general if you take plane wave. And that reflection is also general. So if your case is that I'm not sure if proof is more general or not, but maybe if it's written then you take it. Both are same. if your if potential is same, because reflection and transmission are in the same region. And I think I think I'm not losing any generality. Transmission and coefficient, transmission and reflection are in the same region, so they will have same k. Transmitted can be a different region, although in my case it was same, but it can be a different in general, so I have allowed k to be transmitted to be different. So with that, I can say the current conservation means the total current in the left region is same as total current in the right region. In the right region you have, in the left region you have incident and reflected. You add up k same, you get that. And in the right region you have that, so you put just quantity and then, and now at least maybe no, but still have a generality. K transmitted is allowed to be different. You divide by k, you get here that, and you also divide by a incident square, so the first term becomes 1. 1 minus that, you just work out calculation, and you see this is the 1, this is reflection coefficient, and this is transmission coefficient. So it's 1 minus r is equal to t, so 1 is equal to r plus t. I've given you general proof, but maybe you are not interested to that. That was an optional thing, sorry. But go to the main result. Main problem is that before that I told you the quantum mechanics is not wrong. It does not clash with your daily observation that you cannot cross a wall. And now it's not only it's not wrong, it also predicts something which was which is not a prediction of classical mechanics. And here's the difference, and here quantum mechanics turns out to be right. Now the case is called alpha radioactivity. Before showing telling you what is alpha radioactivity and so on, I first tell you, you can if your result is very surprising to you, the particle can go from here to here without traveling, then I promise you some common sense, and here I can make something like invent a common sense for you here as well. You can think of that the result you don't compare with your traveling through your wall, but you compare it. It's when it is traveling, it's not you traveling, it's a wave traveling. And when it's a wave traveling, and suppose it's an ordinary, as far as wave is concerned, you can use your common sense. The light wave is there, and in between is a region. You think of that, the region is a very thick fog. In that case, what will happen? Light wave will be to the left, some light wave will go to the right. So that means that's it. Here we are saying. Only difference is when you get some light, this light doesn't mean some energy, that means some probability. So that means if it has some probability of appearing here, it has some probability of appearing there, and that is like so probability means it can appear here, and next time, because it's a probability of in the right region, it can appear there. So it's like dice can be a comparison for when it comes to probability, that you threw a dice, first it appeared once, the left region, and then 6 which was in the right region, so something like that. So again I say that I've spoken the quantum mechanics, the only puzzle is the wave function collapse. The wave function is there, it collapsed to left and then it collapsed to right. There's no other puzzle of quantum mechanics. Some people say that there are many puzzles of quantum mechanics. I don't want to make any personal comment on them. It's just there. I think it's only one puzzle is there, quantum mechanics, that is wave function collapse. There is no other puzzle. There are not 5 puzzles. There is only one puzzle in quantum mechanics, and that is wave function collapse. And this tunneling, you say it can travel through a region without traveling, and so that's not a new puzzle. It's just wave function collapse. Now I have kept you waiting for actual physical information, that is alpha radioactivity. The importance is that the quantum is not only that it's not wrong, it does not clash with observation. Also, it makes a prediction which turns out to be different to classical mechanics, and that turns out to be positive. And the prediction is about alpha radioactivity. And first I tell you, for those of you who do not know, I tell them what is alpha radioactivity. And alpha radioactivity is that alpha is a helium nucleus. That means there's a 2 proton, 2 neutron, And if you are radioactivity, that's alpha radioactivity means for example you have maybe 238 nucleon. 4 were split, so remaining you had 234. So what is the potential energy between 4 and 234? You know, the red are protons, so they are positive, and they are also positive, so there's this electromagnetic repulsion. But also there's a nuclear force which is attraction. So this is a combination of attraction and reflection, and maybe I don't have time to, there's a topic of nuclear physics rather than quantum mechanics, so maybe I don't have time to do that. The net result is that you have a reflection, attraction and repulsion. Repulsion means positive potential energy, attraction means negative potential energy. The all in all, the graph is the following. I do not have time to just to give you an argument that this graph is right. You can verify but any books that that is what nuclear physics tells you. Now, if your energy is here and here, if you hope you can pay attention to that, it becomes the 3 regions. Region 1, energy is greater than potential energy. Region 3, energy is greater than potential energy. It's a bit difficult to see that, but you see it or you just take my word for it. Energy is greater than potential energy. In between, energy is lesser than potential energy. So you have qualitatively you have same thing as a barrier. You have 3 regions, region 1, region 2 and region 3. And you have a transmission coefficient. The calculation is complicated, but the only thing is that in that case it was a non-zero transmission coefficient. In this case as well you have a non-zero. Now if you check your understanding, you tell me if transmission coefficient is smaller, okay, my wording is that if your half-life is larger, you know, alpha radioactivity has a half-life. The half-life means on the average, what is the time period of which one alpha particle has to emit. If it emits after a large time, that means the probability of emitting transmission coefficient from region 1 to region 3 is larger or smaller? And the answer is, if half-life is larger, it takes more time, it has less probability that transmission coefficient is lesser. And in conclusion, I don't spend time on it, I just show you, and you can pause the video and see it for yourself, and I think I say thank you to you at that time. Well.